if m equals m tilde modulo gamma as above, and then a gamma invariant metric of course Riemannian metric, let me emphasize, Riemannian metric G tilde on M tilde induces a Riemannian metric. G on M. The proof, we proved it. Proof. If you like, see the discussion of principal bundles. This is a principal bundle. Here, the principal bundle we're talking about is M tilde down to M tilde modulo gamma. It's even much easier here because the fiber is not positive dimensional, so you don't have to have a contraction. Right? You don't contract anything. Right? You just in the invariance condition. That's what it is. So, Cartan knew this. And Cartan, so this is Father Cartan. Of course, knew that the disk, the plane, and P1C have invariant metrics which are invariant with respect to their holomorphic automorphism groups. We just discussed the invariant metric on P1. So on P1, this is the Fognini-Studi metric. On the plane, This is the standard Euclidean metric. And here I have made the group smaller because the full automorphism group, so I lied here a little bit, full automorphism group of the plane, you know that, right? Of the plane, full holomorphic automorphism group of the plane is the affine group, is F1C, and the transformations here are affine, phi of z standard coordinate equals lambda z plus mu, right? The affine group. And of course, this part of it, lambda part of it, does not preserve the metric. It expands the metric, right? It preserves angles, so it's called conformal, but it expands, obviously expands the metric. So that means we really go to just the translation group itself. Now, Cartan is looking to understand this, and Cartan, by the way, well, I knew his son rather well, so that tells you Cartan is not too old. I'm not sure when we're talking about this, maybe also 1920. Early 1900s is when he started thinking about this. So not very long ago. And Cartan also knew understood the disk. So I would like to talk about the disk because in fact the sphere is only the universal cover of the sphere. The plane is only the universal cover of C star with the exponential map or a torus, and the rest of it is the disk. So the disk is the key thing. Okay. What we're going for is this will be constant positive curvature. This will be flat. And this will be negative constant curvature. I haven't talked about curvature, but I will talk about it. Okay? So Cartan also knew the works of Riemann, of course, and he knew that these things had these properties. So he introduced a definition. Definition. What is Cartan's goal? Cartan's goal is to find manifolds which are reasonable under certain curvature conditions. Whatever curvature is, I want to talk about that in a minute. Okay. Whatever curvature is, he says a good condition is that curvature should be invariant under parallel transform. That's obviously a good manifold. Whatever curvature is meaning here, this notion of geometry, this parallel transform, preserving it means the manifold is really good, right? Do you see that you have a vision of that, basically? Yes. Somehow curvature is not changed. So, I have to tell you several things today then. What you know about parallel transform. I have to tell you about curvature. And then I will tell you Cartan's amazing theorem. Okay? Again, he was smart enough to say at the beginning of the subject, this subject is ridiculous. There are too many Riemannian metrics around to be discussing this. We should be discussing good metrics. Yeah. And good metrics should be somehow like the good ones that we have seen on the disk and on the plane. He saw these metrics here. And he says curvature should be invariant on a parallel transform. And therefore, he studied these manifolds for many years. So, let me now go to a chapter on curvature. So, curvature. I haven't talked about what curvature is at all. Okay. Well, the naive viewpoint is the way Gauss was thinking, which was of course very good, is if you take parallel transport along a curve, and then take parallel, that's x, maybe it's parallel transport along a curve x, and then you take parallel transport along y, all right, and then you go back along x. I hope I don't get parallel here. So you go back here, and then you go down here, go around a parallelogram, and you get a mapping. This was Gauss's idea of what curvature should be, is to understand that mapping. Going around, but you can imagine with curvature, you can see it. If you draw pictures of spheres and so on, you go around, this is x, this is x again, and minus x, and it's minus y. So, it's something around, going around closed curves. Yeah, and see what you get. You understand what I'm saying? I haven't written it down yet. Right? Parallel transport around here of a vector, up there, back, and down, that's a mapping. Right? So Cartan introduced a notion called holonomial. I think this is due to Cartan, which is this notion. It's an amazing notion. Right? The holonomic group is equal to the set of G gamma in GL of the tangent space of a base point. So here's a base point here. GL of the tangent space of a base point, which is generated by holonomic, which is generated by parallel transport along gamma. Now, I have not formally written this down very well, but I'm going to say it again. So, call me on this topic. I have a curve from a base point. Okay. if I have a curve, which is piecewise, so because the basic motivation came from parallelograms like this, we allow piecewise smooth instead of just smooth, but I'll draw it smooth. I take a vector here, v, and now I parallel transport it around this curve, and I get a mapping which I'll call G gamma of V. You get it? I go around a closed curve, and I get a mapping V goes to G gamma of V. Okay. So G gamma is parallel transport along gamma. Gamma is a piecewise smooth from the base point. You see it, right? It's very interesting. It's very, very interesting, yeah.
So basically, you take a curve, you take your V, and then when you come back to the point, that's where your G gamma V is.
That's right. Yeah. You just take, so you're quite familiar with this with the fundamental group, the homotopy group, which at the time of Cartan really wasn't invented very much. So this is more complicated than the fundamental group, really. Because not only are you considering all closed curves, you're considering holonomy around this closed curve. It's amazing, right? So parallel transport along closed curves, okay? And it easily seems to be a group. Of course, you need for this piecewise smooth, because if you have two of these things, and you take it around one, and then you take it around another, that's going to be not smooth, obviously, right? It's just going to be piecewise. So this is a group, and if you have, here's P, and here is P hat, and you have some mysterious curve here, gamma, right? Then you do the usual thing that you know how to do with homotopy, is you bring it over here, this is P hat. And you bring it over here, and then you go back here, and you make another curve, but it starts from P hat, right? It's the usual thing. Instead of having this curve gamma here, the curve gamma, this is curve gamma, then gamma hat, you start here, and then you go around gamma, and then you come back. Okay. Yeah.
So the holonomy group just has all the linear transformations that you can get from
That's right.
Any curve.
Any curve. Any curve. Now it's linear. It's clearly linear because parallel transport is a linear is a linear thing.
Can you not get the full thing? Because if you...
He's asking Cartan's question. Cartan said, "What is the holonomy? I mean, classify the holonomy groups that are here,
Yes,
and how are they generated?" That's an interesting question, right? Okay? So classify the holonomy groups that occur, and what generates them somehow, what kind of curves generates them, and so on, right? You're asking that question. That's, in some sense, Cartan's question. Okay. So he has these holonomy groups. There's an amazing thing. These holonomy groups are not necessarily connected. So, holonomy group of a metric. So we need a metric here because this is, well, we need a metric. Well, I don't know. I'm talking about a metric. Holonomy group modulo here's the amazing theory, which I will prove for you. It's not very hard. The holonomy group of the connection is a Lie subgroup That's already very good. I'm going toward your question a little bit, okay? First of all, it's not such a bad group. It's a Lie group. A priori can be something unbelievable. Okay? Okay?
But first you have the linear transformation on the tangent space, right? And
Yes, because you'd start with a tangent vector at that point, and you push it, and you get a tangent vector at that point.
then why is the Lie group subgroup of GL and R and not of the tangent space for example?
Because let me write it here. GL, the tangent space of the base. I was just assuming the manifold's n-dimensional.
Okay.
So, okay. So it's an amazing thing, right? There's at least some group of that. And there is a surjective map onto the holonomy group modulo its connected component. So as you know, a Lie group has many components, possibly. For example, it might be a discrete group. But the stuff that makes it not connected really comes from the fundamental group. You believe it. So you see, if you have something like this, and you go around and you go around that and you go around this and all sorts of things, you have a highly non-trivial curve, which is homotopically highly non-trivial. That will also contribute to holonomy, but it will only contribute to holonomy outside of this connected component. Yeah.
What is the zero? How is holonomy group zero?
Huh?
What does the zero denote?
Connected component at the identity of the Lie group.
Oh, zero is the point.
Okay, the identity.
Yeah.
Yeah, well, we usually write it that way, but I'm sorry, I don't. Okay. Okay. So, going around curves and motivated by going around parallelograms, which is motivated by curvature, is the beginning of a new chapter of our subject, so I have to say what is curvature, I think. Keep in mind the holonomy group. Keep in mind this amazing fact that really the connected component is what's very interesting. It's a normal subgroup. So curvature. I will define two ways of defining curvature. I think curvature is a very deep notion and that we need to think about a lot. First basic notion, basic definition is, it's called R. Guess why we call it R for Riemann. This is the Riemann curvature associated to a connection. So Riemann connection is a mapping of two variables, which Riemann and Gauss and so on probably understood this way. You see, it's very much motivated. X, y minus y, x. Somehow x, y, and then the opposite order, and you come back to the zero. So this, you can see how it's motivated by this parallelogram. Now, this is not quite the definition. I'm sure this was the definition, the way that people like Christoffel and so on discussed the matter, but the correct definition is this. And of course, these guys were computing in using a frame of the tangent bundle where the bracket is 0. You understand, if you take coordinates, if x is in coordinates, you see, usually, so let me just say, bracket, you know this fact, right? You know that fact. And so, in some sense, when you compute, you use some frame like this so that that term does not appear. It's really just the parallelogram. Okay? Okay. This, as you see, is a 1-3 tensor. Why is it a tensor? It's a mapping. So why is it a mapping? So it's a mapping W goes to R, X, Y. Oh, those guys use the letter Z. Z goes to X, R, X, Y of Z. Right? You take Z, you apply, you differentiate it with respect to X, and then you differentiate it with respect to Y. Or you differentiate, it's a commutator. You differentiate it with respect to Y, and then differentiate it with respect to X. It's going around the parallelogram somehow. Okay? I think this was Riemann's definition. Okay. This is called the Riemann curvature tensor. Cartan had the idea that the good manifolds are such that curvature should be invariant under parallel transform. You see, there's no way that curvature is a priori invariant under parallel transform, and you take some arbitrary surface, it's not going to be invariant under parallel transform. Okay? Not curvature. Okay. Now, I don't like this definition because it's highly non-intuitive for me, because in some sense I'm an analyst, and so I like another definition. Okay, I'll make this other definition and then we'll call it quits today, okay? Second definition, that is more or less the same. Robert, you okay on it? Second definition. This definition follows the point of view that I learned from I don't think they're that. Of Chern. I think Chern helped us a lot. I'm not sure Chern invented this point of view, but he helped us a lot by explaining this point of view, because this is very hard to understand. What is a connection? I'm going to use Chern's notation. A connection is a mapping from sections of the bundle to sections of the bundle tensor the cotangent bundle of the manifold. Right? Let's remind ourselves why that's a connection. It satisfies some axioms, of course, but nabla x, then it means nabla x of a section means you take d of this section, and d of this section is a section tensor of one form, and you apply that to x. Right? That's right. Isn't that what it is? It gives you a way of applying x. I mean, this is something I call this the contraction of x of dx. Okay. Now, coming from analysis and learning, the first things I ever learned about geometry from people like Chern and from people like Duron, I said, well, I have an idea. What I like to do here is say, well, we have the sections, and I have D, and I go to the cotangent bundle, that's the differential, and then I want to do it again, and then I go to sections of, oh, I have to hear a tensor with D. E tensor to cotangent bundle, and then I want to do it again. I love doing it again and again. So E tensor, the twofold product of the cotangent bundle, and then do it again and again and again, and so on. Right? You remember we do this with differential forms, right? With differential forms, this is called the Duron Complex. That little tiny d is the trivial connection, and that gives you the Duron Complex. Yeah? This is a non-trivial connection, and so the question is, how am I going to define this guy? How am I going to define this guy? Well, that means no, wait a minute. Yeah, this is how I want to know how to define. I go from here to here, and now I have to define this guy, right? Yeah. Now I'm mixed up. So I want to define the second D. This is the first D here. So how do I define this D? So D of a section tensor a form omega. Oh yeah. How would any idiot define this? Well, this is a form and this is a section. This is here, section and a form. Well, that's D of the section, tensor the form, or wedge the form, plus the section, wedge D of the form. What's D of the form? D. No? Isn't that the obvious way to define that? No? So this has to be reasonable with respect to the section, with respect to forms. D of a section times the form, section times D of the form. We have the trivial connection on forms, we use it here. So if we have a connection on something and a connection on another thing, we have a new connection on the tensor product, connection on the first, wedge the second, first wedge connection on the second. This is of the form D of let's say A, B tensor B equals D1 of A tensor B plus A tensor D2 of B. And you have two connections. We have a connection on sections, we have a connection on the differential form. This is the connection that God gave us, or somebody gave us to study differential geometry. And here's the connection, trivial connection on the forms. Okay? That's the natural thing.
S, which the omega isn't so. The wedge product is only defined for forms.
What?
The wedge. So S wedge the omega isn't the wedge only defined for forms. So
That's
S,
right. This is really, this is wedge because that's a,
yes.
maybe this is just, yeah. Okay. Okay, we're getting tired now, but isn't this a natural thing to do? And then the natural thing to consider is d squared. Right? So you take the connection, you extend it, you can continue doing this if you want, but I think the most interesting thing is you do it twice. Okay? You do the connection and then you do the extended connection by this rule and you get d squared. Okay? This thing is often denoted by F. And this is called the curvature. And it's often denoted by big omega, which is often called the curvature. So if you see in the literature F or big omega, my colleagues usually call, and friends usually call it F. Okay? Now, we have maybe 10 minutes. I would like to speak about properties of F. So I will show next time. This is an obvious thing. This complicated business here with parallelograms, it requires some deep thinking, for me anyway. This is an obvious thing. This is an extension. This is not a complex. D composed with D here is essentially never zero. It's only zero in the case of the trivial D. Okay. Curvature is the obstruction to that thing being a complex. Right? It's an obstruction to doing Duron cohomology. Okay. So, interesting fact. I will show you next time that F, I will call it F, is essentially you have to think of it in the right way, R. So there's nothing really different from this mysterious parallelogram thing. I have to explain that to you. You just have to think in the right way. It's essentially the Riemannian curvature. Two, if omega is the curvature matrix of D. If omega is the curvature matrix of D, let's remember what this is. We've forgotten all this stuff. I mean, it takes, we get tired and forget. This means you have a frame, E, and D of EJ equals EI tensor omega IJ. Then omega is this matrix of one forms which is omega ij. That's the curvature matrix. That's the connection matrix. So let us write omega, it depends on the basis on the frame E. Right? You get a matrix, it depends on the frame. Frame change, as you know, it's called change of basis, is E goes to E hat, which is a new frame, and you should think of it being, say, if the matrix is called G, frame change, you really should think of G multiplying on the right of this vector E. So that's the frame change. And then you will check something terrible. I don't know whether we've talked about this or not. How does the new thing look after the frame change? Right? How does it look, you know? This equals G inverse, that's a matrix. This is a matrix. G inverse dg. That means take d of all this stuff in the matrix and take d of that's in one form, plus G inverse omega e g. You could check it. This is stupid to check. Okay, you just write down what it is. That is, I hope you understand. That's a terrible transition. That's an affine map, and it makes sense because you know the whole space is an affine space we're dealing with. This is an affine map, right? This is a wonderful linear map here. Okay. This is an affine map. In particular, this says that this thing is not a tensor. Okay. Now, the curvature matrix maybe I'll call that big omega. So it's the matrix associated with this thing, yeah, of this form D squared. It's a matrix of two forms. Matrix of two forms. Same definition as above for one form, of two forms. And we should write, if it's based on some E, some frame, some basis of thing, you can compute it, believe it or not. It's wonderful. D omega plus omega wedge omega. Isn't that beautiful? What does it mean, omega wedge omega? That means you take the matrix omega and just multiply it with wedge product. This is multiplication with wedge product. And this is just D of all the entries in that. That's a wonderful thing. But even more wonderful, is the influence of change of frame. Change of frame so omega of E hat, where E hat is given to us by a frame change G, cannot be better. So the good thing to consider, believe it or not, is curvature. The connection is something really bad from the point of view of frame change. Curvature is wonderful from the point of view of frame change. You could not ask any, you understand what I'm saying? Right? You have a vector bundle. The frames are being changed by the transition functions of the vector bundle. Right? You have curvature defined in local trivializations. That gives you omega. You change frames, it looks like this. Right? Now, as a final remark, what are the invariants of conjugation? That's a 2 by 2 matrix. This is a 2 by 2 matrix, right? No, not two by two. It's a matrix of two forms. Excuse me, a matrix of two forms, not two by two. Yeah. Can you tell me an invariant?
Determinant.
Huh? Right. Bravo. Determinant. Yes. That's called the top Chern class of this bundle. It's a differential form. You go to the Duron class of that and so on, and you get a top invariant. This is called. So the invariant. I'm really happy that you said determinant. Now we'll test whether or not you got a good linear algebra. What are the invariants of conjugation of a matrix? You know another one? No, I don't know. Somebody else? Another invariant of conjugation of an operator.
And the basis of the equal state.
Basis independent.
Trace.
Great. Another one. I bet you lose, I bet you can't get any more. Trace is an invariant, right? Determinant's an invariant. Right? What is trace? What is determinant, by the way? What is determinant? It's the top wedge product of the operator, or? Well, it's the top wedge product of the operator, is it not? Have you ever done that calculation? Take a vector space. Okay, here's my suggestion for a calculation. Take a vector space of dimension n. Take the top wedge product of the vector space. That's the n-fold product of the vector space. V, tensor wedge, right? That stops at dimension 1, okay? Right? The top wedge product is one-dimensional. If you have an operator, I'm glad you're pushing this a little bit. Let me just write so we can discuss this, and then I'll let you go. It's too boring for you probably. If we have an operator A from V1 wedge, maybe not the top. How does that act? It acts like this, right?
Isn't it just something times the determinant?
Well, the K is not necessarily the top.
K is not necessarily the top.
Okay, for K equal the dimension of the vector space, then the top wedge product is one-dimensional. Right? Okay. So that means that this, so in that case, that means that this is a number times this thing. Right? It's a number of that thing. Right? Okay. Any guesses what that number is?
Determinant.
Right. But it's the trace of the top wedge product of the operator. It's because the trace is a trace of a 1 by 1 matrix is the matrix itself. Okay. So the invariants, please you physics people listen to me, are these. If you have an operator on a vector space, you have the operator on all wedge products, and you have the trace of all of those wedge operators, right? Okay. Right. And now, somebody here already said it. I don't know who, somebody said the word eigenvalue. And therefore, you look at the characteristic polynomial in Z of the operator A, this equals up to sign Z to the n minus some coefficient C1 C1 of A Z to the n minus 1 plus and so on, and then it depends, plus minus C n n times number 1. That's a characteristic polynomial. Right? Okay. What are those numbers? You know the numbers by heart? The last one, I hope, is the determinant, right? Right? These are those numbers. And those numbers generate, so here's the theorem. And in case you have not proved this theorem, this is the first theorem in linear algebra. The polynomial invariance of conjugation on linear operators on a finite dimensional vector space are generated by these operators. That means that every polynomial invariant of conjugation is a polynomial in these operators. That means the ring of invariant polynomials is the ring generated by these operators. Freely generated, by the way. You get it? You didn't know that. It's very, very important. Because that says, if you have a vector bundle with a connection, and you go to the curvature, and you want something that's invariant, all you need to do is apply to get everything. You apply trace of the k-fold wedge product of the curvature. Okay. Those are the fundamental, they will generate the so-called fundamental characteristic classes of the bundle. They're characteristic of the bundle, huh? Yeah. Well, they depend on the connection and so on, but actually they don't, if you go to cohomology. Is that not interesting? Yeah. Okay. This point of view we learned shortly after World War II, I think, in particular from Chern, and maybe also from the lectures of Andre Weber in Göttingen. Okay, see you next week. We have one more lecture before we have a break, but that's what we talked about, right? Yeah. Next week we have it, and then after that, great. 4 lectures. Okay, great. Thanks for.